Hello, pre-calc honor students. Here are with 6.4 hyperbolas. Now, what's the objective? To find the equations of hyperbolas and to graph them. What is the geometric definition of a hyperbola? Well, that's tricky, but it's just a slight variation on what we saw before with the ellipse. It's a set of points whose difference of the focal radii, or ditver, is constant. This ditver ends up being the distance between the vertices, and it's equal to 2a. Just like the distance between the vertices on an ellipse is 2a. Now, hyperbolas require two foci, just like ellipses. And the focal radius, we talked about that before. It's the distance from point to hyperbola. Now, here are the A, B, and C's of hyperbolas. A is used to find the vertices as you would in an ellipse. And they align on what's called the transverse axis, because this actually crosses the hyperbola at the vertices and contains the foci. So the center, foci, and hyperbola are all on the transverse axis. The center, foci, and center are all on the transverse axis. B is used to create the box of extent on the conjugate axis. And we're going to do an example of this in a bit. But this axis ends up being perpendicular to the transverse axis. It actually goes between the two branches of the hyperbola. And since it never crosses it, it's called the conjugate, because if you tried to find the answers, they'd be imaginary. Finally, part C is the distance from the center, HK, to either focus, just as we saw with the hyperbolas, the ellipses. But now, in this case, with the hyperbolas, the foci end up being outside of the box of extent, outside of the vertices. And also, whereas we saw with the ellipses, a squared equals b squared plus c squared, now we have in hyperbolas c squared equals a squared plus b squared in hyperbolas. Let's try and graph some of these. Oh, but first, again, this is available in that section I talked about the other day, involving, it's called Handy Forms, and it's on the website. We have two kinds of hyperbola depending on how you stretch out. Notice you can have the hyperbola can be vertical if the a is underneath the y's. It's horizontal if the a is underneath the x's. And also notice what comes first here in the subtraction. You get a vertical if the y squareds are coming first, so subtract from the x and subtract the x squareds. And if the x squareds come first and subtract from that, it's horizontal. And here's our various tricks for coming up with the vertices and using B to form the box of extent and so forth. Ditver that we talked about before. Focal width is still 2b squared over a, just like in the ellipses. Now the eccentricity, though, is greater than 1. And also in hyperbolas we have asymptotes. So let's talk about those. You're going to get the asymptotes by forming the box of extent and making the diagonals of the box of extent, which will cross at the center, HK, and then those can be used then to come up with the equations of your asymptotes. Now, let's graph this hyperbola and find its foci. This one is conveniently doesn't have any shifting off the center at the origin, so the center is just at 0, 0. And we can write this as x squared over 6 squared minus y squared over 3 squared equals 1. And let's come up with a decent graph for this. A couple of graph paper. My content. Graphing. Here we go. No graph paper. So we have our center at the origin, and we're going to put points at 6 each way in the x. 1, 2, 3, 4, 5, 6. And back 6 in the x. So those are the vertices at 6, 0 and negative 6, 0. We also have something at 3 each way in the y, but I'm going to put open circles there because those are actually part of the conjugate axis. And that's using the b then to come up with a point on the conjugate axis. And now these form the box of extent. So we can put dashed lines into here. And it's the corners of the box of extent that we're going to connect now with diagonal lines. I think I have that option here. Yeah, let's make some dashed lines. Oh. Let's try that again. There's another tool in here that actually makes the line. There we go, that's what I was looking for. Here's our nice asymptotes. Maybe we got to just move that one over a little bit. There. See how they cross at the center? At the center, 0, 0. And then finishing up the hyperbola, we can put in like this and show how it gets closer and closer to the asymptotes. Now these asymptotes would have equations would be at y equals plus or minus, now look at the slope, you're going over 6 and up 3, so it's a slope of 3/6 times x. The center's at 0, 0, so basically y equals plus or minus a half x. Become our two asymptotes. Now our next example, graph the hyperbola and its foci. X squared over 9 minus x, y squared over 9 minus x squared over 3, 6 equals 1. So we can get it in the form again. The center is going to be at 0, 0. So we have y squared over 3 squared minus x squared over 6 squared equals 1. And essentially, we can copy what we did the other time here, because we have the same box of extent. And so, there we've got a clone of the page. Just want to move this page over though. Get these clones separated here. Oopsie, now it did it. Move this over here. Okay. No. Okay. Move this page. Let's see what the problem is. Move this page right there. Okay. And that almost worked. That's that graph. Here's the new graph. Almost. We want to get it after that. There we go. So here we go. Now in this example 2 parabola, instead let's do this one in black. We're going to find our vertices at 0, 3. And these guys here and here. And it's going to go this way and spread out vertically instead of horizontally. And now you can see that where are the foci? That's right, we forgot to do the foci on both these. C squared equals a squared plus b squared. So c squared equals 9 and 36, which is 45. And c is the square root of 45, or 3 square roots of 5. Puts you right around 6 something. So the foci, 1, 2, 3, 4, 5, 6 up here, and down 6, 1, 2, 3, 4, 5, 6 and a half or so. There are your foci. And we can also add to this the focal width is 2b squared over a. So that's b squared over a each way. So b squared is 6 squared, so it's 6 squared over 3, 36 thirds, or 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Way out here. Yeah, that seems to work. And also up here, come over 12. 9, 10, 11, 12. There's our endpoints of the focal width. Let's go back and make sure we had the foci here on example 1. C squared is still a squared plus b squared. So c squared equals 36 and 9. C squared equals 45. So C equals the square root of 45, which is essentially 3 root 5. And that's a little less than 7, somewhere around 6.7. But the foci end up in this direction, 1, 2, 3, 4, 5, 6, a little more than that. There are your foci, again, outside the box of extent, lining up with the vertices in the center along the transverse axis. And the focal width is going to be much smaller because the focal width is 2b squared over a. So that's twice b squared is 9 over a, which is 6. 18, 6 is 3. So we're just going to go 1.5 each way. There's your 1.5, and there's your other 1.5. 1.5. Oh, should get that picture a little better. There you go. And 1.5. All right. Now, let's get to a homework problem. Sketch the hyperbola equations given and find the coordinates of the vertices and the foci and the equations for the asymptotes. Wow. Well, the big pain on this one is that it's not in what we call our standard form. So we have to separate the variables. No big whoop. X squared minus 2x plus blank minus 4y squared plus 16y plus blank equals 19 plus blankety blank. Well, to complete the square here, I'm going to take an extra step first here. This one's pretty straightforward, but we should factor out a minus 4 from these two, leaving y squared minus 4y plus blank equals 19 plus, and we're going to have 2 more things to add in over here. So let's see what we add in. We add in 1 for this, so we add 1 to this side. And here, y squared minus 4y, the complete square would be 4 here, but it's 4 times negative 4, so we add in negative 16. So we end up with x minus 1 squared plus negative 4 times y minus 2 squared equals 4. So that ends up being, whoopsie, nope, x minus 1 squared. I'm going to divide both sides by 4. Divide by 4 to get 1 on the right. So we get x minus 1 squared over 4 minus y minus 2 squared over 1 equals 1. And so our a is the leading one, that's 2. B equals 1. C squared equals a squared plus b squared. So c equals the square root of 2 squared plus 1 squared. So c is equal to the square root of 5. So we should be able to locate things. We also have our center at 1, 2. And I believe I have, yep, it graphed out for us here. There we go. Let's get all these details in here. The center at 1, 2. Sure enough, there's our center of the hyperbola. Vertices then. Vertices at, we're going to go from the center plus or minus a. So 1, 2 plus or minus 2, 0. So we have vertices at 3, 2 and negative 1, 2. To be sure, there they are, 3, 2 and negative 1, 2. The foci are going to be at the center plus or minus center plus or minus c. So 1, 2 plus or minus square root of 5, 0. So the foci are at 1 plus the square root of 5, 2, and at 1 minus the square root of 5, 2 for the foci. Now we can use b equals 1 to come up with these points here and here. Come like this. That's our box of extent, and here are the diagonals of the box of extent. Now you can see a much better job what's going on here when if I switch over to GeoGebra. Here in GeoGebra, I actually have it displayed in both this format, the standard form, and also the center form. And you can just right-click on your things and you can switch back and forth between the two types of equations, standard form or centered form. There's our center. Let's get that center located at 1, 2. Got our center at 1, 2. We also have the vertices at 3, 2. And at negative 1, 2. There are your vertices. Then we also have, like we said, go up 1 in both directions. Use this B, this underneath the Y here. We're going to go 1 each way in the Y direction to come up with 1, 3. And 1, 1. Now, a lot of times kids unfortunately make their box of extent by connecting these. No, these become the midpoints of the side of the box of extent. So we actually want to go ahead and put in segments like this. There. And snap into grid here. There. There. Now we can put in our equations of the asymptotes. And they'll go from the diagonals of the box of extent. Boom. And boom. And we should make all these dashed. So all these things. This, 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 this. We want to make all those dashed. And we didn't get quite to all of them. I will edit this out. And there you go. That's what it should look like. Okay. All right, back to our notes now, the doozer problem. Just pop this in here. That's a really pretty graph. And also, well, we were asked to come up with the actual equations of these asymptotes. Yep, the equations of the asymptote. We found the foci. We found the vertices. Now here are the equations of the asymptotes. For the equations of the asymptotes, you use the center, which in this case is 1, 2, and then the slope is going to be based on A and B, and I can just look at the picture here, how much we're going over and how much we're going up. We're going over 2 and up 1. So the slopes are plus or minus a half. They come in just opposites of each other for both horizontal and vertical parabolas. So in this case, we get then for the asymptotes y minus 2 equals plus or minus a half times x minus 1. Real handy application of point slope form, where you can use the plus or minus slopes right there, and then just use the center, because each of the asymptotes goes through the center. Okay, pre-calc counter students, here's a doozer that you can start working on, and we'll go over it in class. Find the equation of hyperbola with foci at negative 1, 2, and 7, 6 with one vertex at 1, 3. Sketch it and also find the asymptotes. Well, this is quite the doozer. And we're going to have to go back to the geometric definition of hyperbola to actually do this. First, let's look at it in GeoGebra. I used this tool in GeoGebra, the hyperbola drawing tool, where you specify the foci and one point on the hyperbola. Here are the foci at negative 1, 2, and at 7, 6. And also I put this point 1, 3 as one of the vertices. And that's how I'm actually changing the size. Point D is just an arbitrary point on the hyperbola. And I'm actually showing the focal radii here. And the focal radii keep changing, but the difference in the focal radii over here and C here, that stays the same. Okay? So, hopefully you recognize that 4.47 is 2 root 5. I set up C in such a way that you can see right here, when I show the transverse axis, here's the midpoint right there at 3, 4 is the center. And the distance from the center to the vertex is A. So that's over, down 1 over 2, so that's the square root of 5. So 2A is 2 root 5, and that is our ditfir. Our ditfir is 2 root 5. So let's jot that down on our notes then. We have that the ditfir, the difference in the focal radii, equals 2A. Okay? And in this case, that was equal to 2 root 5. A was equal to the square root of 5, and so we get 2 root 5. And then we had foci at negative 1, 2, and 7, 6. Negative 1, 2, and 7, 6. So the distance between those, so the square root of x minus 7 squared plus y minus 6 squared minus the square root of x plus 1 squared plus y minus 2 squared, that has to equal the ditfir, which is 2 times the square root of 5. Okay, now all I have to do is expand that out, and our goal is to eventually reach what we see here in GeoGebra as the algebraic answer, and that's right here. Look at that monster equation. It's got an xy term because it's been twisted. You can't use your typical things for this. So let's capture that and put that in our big sheet. Let's cut this out. Cruise down here. Put a few sheets in between, because believe me, it's going to take a lot of work to get there. Can we get that? Maybe we can work on dividing it out and so forth. Well, I'll have the solution later, and I'll post it. You can start trying to work your way through that algebra, and I'll have it posted on the wiki space under this site. Right now, just got to stop the video.